Hello everyone. In this section of the video, we will discuss refrigeration system. We will learn the different components and parts of the refrigeration system. We will also learn how to conduct a performance test on a vapor compression refrigeration system.
In the next few slides, we will see the basics of refrigeration systems, principle and working and performance of vapor compression refrigeration system. Refrigeration systems has plenty of applications such as air conditioning, simple refrigerator at home, domestic refrigerator, freezers, etc. There are many types of refrigeration systems based on Rankine vapor compression refrigeration cycle. It can be classified as vapor cycle and gas cycles. Again, it can be classified as vapor compression refrigeration and sorption refrigerations. Sorption refrigerations can be again classified as vapor absorption refrigeration and absorption refrigeration systems. There are plenty of other type of refrigeration systems. Vapor compression refrigeration system is the most commonly used refrigeration system. In this case, in the compressor of a vapor compression refrigeration system, vapor state of the refrigerant is compressed, and that's why generally it is called as vapor compression refrigeration systems. A simple home refrigeration system is also a vapor compression refrigeration system. We will see its principle of working later. Vapor absorption refrigeration systems make use of the same concept. However, it uses a different refrigerator which is having a high affinity towards water, such as that of ammonia. An ammonia absorber and along with the pump together forms and replaces the compressor of the vapor absorption refrigeration system. Absorption refrigeration systems are generally used for high refrigeration effects such as ice making plants. Vapor compression and absorption refrigeration systems are also used for many other applications such as central air conditioning system, where chilled water is made using a refrigeration system and it's circulated around buildings to cool whole building systems. Components of refrigeration systems are as follows. We have a refrigeration experimental setup over here, and we will see what are the different components in the few slides. First one, the compressor.
This is a test run of a low start torque domestic refrigeration compressor to demonstrate the lubrication system.
The whole setup is inserted in a coolant. You can also see how the refrigerant moves.
It's going everywhere. Very effective. Okay, I'm going to switch this off.
So this is how the compressor works.
That is just everywhere. This is test of a low start torque compressor with a high starting torque relay and 60 microfarad start capacitor. This may or may not work. I haven't done it yet, but let's give it a shot. Hey, it does work. Doesn't seem to be doing anything bad. Okay.
Higher the star ratings of refrigeration systems and compressors, the lower the amount of air. Before the condenser, the refrigerant is a vapor, and after the condenser, after throwing down the heat, it cools down to a liquid. And now the values of pressures before and after the compressors remain the same. However, the compromise of temperature even at a closed circuit is done because of the state change from vapor to liquid. Throttling valve or the expansion valve. Here we can see the throttling valve. In this refrigeration experimental setup, we have two throttling valves. One is a capillary type here, and a thermostatic and the thermostatic expansion valve here. How does the throttle valve work? It's a simple opening of a very small diameter, and in the constant volume circuit, the circuit volume is constant and the refrigerant never comes out of the circuit. As we see the working of a simple deodorant bottle. When the plunger is pressed, the high pressure liquid comes out, it gets suspended in air, absorbs the heat and then turns into vapor. The same principle happens over here. Now let's see the working principle of vapor compression refrigeration system. Here we have two circuit diagrams, then we have the enthalpy diagrams over here. In a vapor compression refrigeration system, the parts compressor, the condenser, the throttle valve, the evaporator coils, and back to the compressor. In the compressor, the refrigerant, which is a vapor, is absorbed, sucked inside and compressed to high pressure and temperature. As the pressure increases, the temperature also increases as per the laws of thermodynamics and gas laws. And the high pressure, high temperature refrigerant enters the condenser. The condenser is a heat exchanger and exchange heats to the surroundings, and now the pressure remains the same. However, the temperature drops down and the refrigerant becomes a liquid. Now the compromise of the pressure remaining same and not the temperature is done by another compromise, such as that of the state change from vapor to liquid. In the throttle valve, we have the refrigerant pressure dropping down to very small values, and as the pressure drops down, the temperature also drops down here, and the state still remains the same, but it is in a suspended state. And then the refrigerant goes to the evaporator. In the evaporator, it absorbs heat from the surroundings. In this experimental setup, we are extracting heat from the water, and then when it absorbs heat, it becomes a vapor, and the circuit continues. Point number 1 to 2 is represented as compression. In a refrigeration, compression is electrical work done by the movement of the compressor coil and increase of pressure from low pressure area to high pressure area. 2 to 3 is condensation, or the extraction of heat from the system to the surroundings in the circuit. 3 is the expansion, so what happens in the throttle valve, 3 to 4, and back to the circuit. In a refrigeration system, you will always have two major pressures, high pressure and low pressures. The high pressure is after the compression or after the compressor, before the throttle valve. At the throttle valve, the pressure is dropped down. So high pressure region here and low pressure regions here. The different types of thermostatic expansion valves have different working, and they are used for different applications. Their working principles are given here. Evaporator coils. Evaporator coils are the place where the refrigerant exchanges heat of the refrigerant after the throttle valve and extracts heat from the surroundings and changes its states from a liquid or suspended to a pure gas vapor regions. In a home refrigeration systems, the evaporator is around the freezer. There's some pipes over here. If you put your hand underneath, and you'll see that there are pipes, there's evaporator pipes, and from there you have the most cooling, and then the cooling gradually decreases as the lower part of the refrigeration system. The refrigerant is the mechanism to absorb heat, to change its states at different points, and also to throw away the heat. The heat transfer takes place because of the refrigerant. So here we can see the refrigerant moving in the rotameter over here. There are many types of refrigerants. Commonly used are ammonia, carbon dioxide, sulfur dioxide, methyl chlorides, and freons. Freon has been the most commonly used. However, the freons have an chance to go and meet the ozone layer. It can kill the ozone layer by forming chlorine gas. So freon can combine with ozone to form chlorine. So today we have the freon compounds replaced with an HFC and a HCFC. The hydrogen H holds the CFC together and binds it so that it does not react, and therefore the ozone layers are safer today. Now let's see how to conduct a performance test on a refrigeration system. We will find the refrigeration effect and the COP. Let us see the procedure step by step. First, in the refrigeration experimental setup, before switching on the compressor, the experimental setup is switched on, and the evaporator temperature is taken first. So the evaporator temperature first is T1, it is 28.5 degrees Celsius. How to take the evaporator temperature? Evaporator is chiller, it is T1 here, chiller water temperature. So we have to turn this temperature knob to T11. We have to turn the temperature knob to T11 and take down the temperature of water. Here it is 28.5 degrees Celsius. We also need to find out the final temperature at the end of the experiment, which is T2. At any point of time, the evaporator always needs to be in contact with water or a cooling substance. In this case it's water, and it is measured as 10 liters of water. So therefore the mass flow rate is 10 kg per second. The second step, we find the compressor run time. The compressor run time is the time taken for the duration of the experiment. We use a separate stopwatch for this. Now the compressor is switched on and the stopwatch is also switched on together. At any point of time until the experiment is not over, this stopwatch is not being used for anything else. Next, find the energy meter readings. How to find the energy meter readings? Take another stopwatch and look at the disc over here, and when it reads red, start counting. Now the counting has started, and when it rotates and becomes 1 revolutions, loudly say 1 and keep on counting it loudly so that the number is not missed. Take the readings for 10 revolutions, n equal to 10 or n equal to 5. Higher the number of revolutions, better is the accuracy. Next is to take the pressure gauge readings. How do you take the pressure gauge readings? Let's see how to do it. So the pressure gauge readings, the pressure points are there on the experimental table. So let us find out what are the pressure gauges. We have mainly 2 pressures, high pressures and low pressures, and we have 4 pressure gauges readings to be taken, but there are plenty of pressure gauges. That is okay, but we only need 4 pressure gauges, and we only need 2 pressures or 2 pressure gauge readings to find the theoretical enthalpy. So pressure gauge 1, P1, is inlet to the compressor, P2 is outlet, and similarly 2, 3, 4 point numbers are given over here. So let's take an example how to note down P1. So P1 here is inlet to the compressor. In the experimental board, inlet to the compressor is T10, number 10. So I will go ahead and look at the 10th gauge over here and see what the reading is and write it for P1 here. So the pressure points corresponds to the pressure gauges. This number does not correspond to this value. How to take the pressure gauge readings? Look at the pressure gauge. We will look the innermost circle. The innermost circle is PSI, and it is here black here. 0 is here, and we have 50 PSI, 100 and 150 PSI, 0, 10, 20, 30, 40, 50. In this case, the needle is in between 20 and 30 PSI, so approximately 24 PSI. Now next, take down the temperature readings. The corresponding pressure readings are also the corresponding temperature readings. For example, P1, the temperature is T1. So temperature sensing points, I need to look out inlet to the compressor. So inlet to the compressor is T10. So I have to look at T10 to find T1 over here. So I change the knob to T10 and write the value over here. Similarly, all the other 3 temperatures are written down. Now finally we fill the tabular column. We have the gauge pressure in PSI, we have written it over here. We have the P3 going to the highest high pressure. Then we have converted the pressure into bars. 1 bar is so many PSIs. And then we have taken the absolute pressure. Absolute pressure is gauge pressure plus the atmosphere pressure, which is 1. So finally we have written the absolute pressure in megapascals over here. We need this pressure in megapascals so that we can refer the chart which is also in megapascal. So this is how we have note down the tabular column. Finally, at the end of the experiment, we also note down the final temperature of water by using the stopwatch which has been switched on in the beginning of the experiment. These are the enthalpies, and we will now learn how to find the enthalpies. These are the calculations to find the refrigeration effect. So how do you find the refrigeration effect, and how do you find the energy supply to the unit? Energy supplied to the unit is E, number of revolutions 3600, time taken, and energy meter constant, which is 750. The energy meter constant is given in the energy meter. It is 750 revolution per kilowatt hour. It has a meaning that when the disk rotates 750 times, you have 1 kilowatt hour or 1 unit of power consumptions. So kilojoules per second is kilowatt, kilojoules per second kilowatt. And finally the refrigeration effect, which is MCP delta T, the temperature initial and the final temperatures difference. N is the amount of mass flow rate of water at so much interval of time. So this is how we have found. Again, it is kilojoules per second, which is kilowatt. Now to find the coefficient of performance, it's defined as the desired output as the required input. The desired output is the refrigeration effect. The required input is the electricity. Since in the refrigeration system we are comparing electricity and heat, we have two different benchmarks. Therefore we don't use efficiency. COP is used whenever electricity and heat is compared, that is high grade and low grade. Efficiency cannot be used. So actual COP can be found out by the refrigeration effect divided by the energy supplied, and it's a value greater than 1. Now let's see how we can find theoretical COP. To find the theoretical COP, we need to first understand how to read the refrigeration chart. The refrigeration chart is over here. Let us see the point numbers. In this case, P1 is point number 1, which is here. P2 after compression, where electricity is provided, 1 to 2, 2 to 3 condensations, 3 to 4 throttling, 4 to 1 evaporations. Now point number 1, 2, 3 and 4 are to be located in the refrigeration chart over here. Now in the refrigeration chart, let us look at the refrigeration chart. We have the cooling curve here. The cooling curve has a critical point. On the left side of the cooling curve we have saturated liquid line. On the right side we have vapor lines, and we also have a constant or isoentropy line over here. Now why vapor, why liquid? These relates to the refrigerant conditions. At point number 1, the refrigerant coming out of the evaporated has extract all the heat and changed its state into vapor, and that's also the same state after compression. However, after condensation it has lost heat to the surroundings and become liquid, so therefore it is a liquid state. So we call it as dry state here and liquid state over here. So now let's look into the refrigeration chart. In the refrigeration chart we are looking pressures in megapascals and enthalpies in kilojoules. We have the cooling curve here, the critical point here. So now let's look into the tabular column and find out the regions of high pressures and low pressures. The high pressure regions, the first pressure is 0.271 megapascals. 0.271 is around this place. So I will draw a line to the vapor region and then vapor cooling curve, and I will drop a perpendicular and I'll get the enthalpy. So this is the enthalpy, around 390 kilojoules per kg. Now go for the higher pressure. The higher pressure is 1.469 megapascals. 1.469 megapascal comes here. Draw a line here again to the dry side, and then from the point number 1 identify which is the nearest parallel line or constant entropy line. So I see that these are the constant entropy line, and the nearest constant entropy line to point number 2 is this one. So what I'll do is I will draw a parallel line holding a scale to this line and then extend the high pressure line to that line. So I will get the point number 2 over here by drawing a parallel line to the nearest constant entropy line, and then I will drop a perpendicular, I will get the H2 value, which is around 430 megapascals. Now to find H3, it is in the liquid region line, so I will drop a line from here to the back side to the liquid cooling curve side, and then when it comes back over here, I will drop a line to the enthalpy, drop a perpendicular here and get H3 value. H3 is equal to H4. So this is how we have got point number 1 enthalpy here, point number 2 enthalpy here, 3 and 4, all the points. Finally, we calculate the theoretical COP as the ratios of enthalpies at different pressures, and we will see that we get a value greater than that of the actual COP. The relative COP tells us how well the actual COP matches with that of the theoretical COP. So this is how we conduct an experiment on refrigeration system.
With this, we have come to the end of the video. We have learned how to conduct a performance test on the refrigeration system. We have learned a few concepts and parts and description of a refrigeration system. Thank you.